Polarization mode dispersion. This is the last kind of dispersion that we are going to discuss. Polarization mode dispersion is a source of pulse broadening which results from fiber birefringence, and it can become a limiting factor for optical fiber communication at high transmission rates. It is a random effect due to both intrinsic, caused by non-circular fiber core geometry and residual stresses in glass material near the core region, and extrinsic, which is caused by stress from mechanical loading, bending, or twisting of fiber. So extrinsic factors and intrinsic factors are there, which in actual manufactured fiber result in group velocity variation with polarization state. The time domain effect of polarization mode dispersion in a short fiber length with a pulse being launched with equal power on the two birefringence axes. This is one, this is another. These are two birefringence axes, x and y, becoming two pulses at the output separated by differential group delay. Basically what it is meaning that along y direction and along x direction we have uh, different velocities, right? Different velocities. So here we have fast velocity and here we have slower velocity, lower velocity. So they are starting at the same time, but when they are reaching at the destination or after traversing certain path length within the fiber, this particular mode will have a higher velocity and it will reach earlier, and this mode will be slower mode and it will reach later, so effectively increasing the uh, duration of the pulse. So delta tau g, the amount of pulse broadening, equal to delta tau by L, that is dw of beta x minus beta y. Beta x and beta y are the phase coefficient for x direction and y direction, that is x axis and y axis. So d omega of omega nx by c minus omega ny by c, that means d omega of omega by c into delta n effective, that is delta n effective by c minus omega by c d omega of delta n effective. So delta tau g is the differential group delay per unit length, referred to as the polarization mode dispersion of the fiber, and is usually expressed in units of picosecond per kilometer of fiber, such that the differential group delay is the time domain manifestation of polarization mode dispersion. For conventional single mode fibers, the axis of birefringence varies randomly with along the fiber. So this phenomena causes polarization mode coupling such that the fast and slow polarization modes of one segment of long fiber migrate into both fast and slow modes in the next span because of the change in geometry. The polarization coupling, which results from localized stress during cabling, from splices and connectors, and from variations in the fiber drawing process. During fabrication we have to draw the fiber, so during that process it tends to reduce the overall dispersion because the PMD effects do not accumulate linearly in a very long fiber span. So we can use polarization maintaining fiber. Different type of polarization maintaining fibers are there. Polarization maintaining fiber structure like elliptical core, so it is not circular core, it is little bit elliptical core. Side pit fiber, this one. Then elliptical stress cladding, this one. Then bow tie stress region, this type of circular stress regions, which are this one is also called the panda fiber. And then flat fiber like this one, twisted fiber. So we have some twist right here and right here. So various kind of polarization maintaining fibers may be used to reduce this polarization mode dispersion.